Welcome back. So, today we are going to go over two of the problems which appeared there in the last assignment. The first problem is related to finding out the average of cosine of angle between successive jumps in a BCC crystal structure. So, let us try to evaluate average of cos theta I plus 1 in BCC. So, just a recap of how Manning defined various jump frequencies of vacancy in a BCC structure. This is what we have already seen in one of the previous lectures. So, I have shown two adjacent BCC unit cells here. On the left side at the body center where the vacancy is located, and our tag datum x is at one corner here. So, Manning defined the frequencies as follows. Now, there are 8 nearest neighbor for the vacancies, which all of them lie on 8 corners of this cube. One of them is of course the tag datum x, and the frequency of exchange of a vacancy with the tag datum is defined as omega 2. So, omega 2, it is this jump omega 2. So, omega 2 is the frequency of exchange of a vacancy with the tag datum x. Then there are 3 nearest neighbor of the vacancy, which are the second nearest neighbor of the tag datum. They are denoted by number 2 here. So, the frequency of exchange of the vacancy from the nearest neighbor site of x with an atom on the second nearest neighbor of x, this frequency is denoted as omega 1. So, omega 1 is the frequency of exchange of the vacancy on nearest neighbor with an atom on second nearest neighbor of x. So, this nearest neighbor and second nearest neighbor are those of x. Then reverse frequency can be defined if the vacancy jumps from the second nearest neighbor to the nearest neighbor. It is defined as omega 1 prime. So, omega 1 prime is the frequency of exchange of the vacancy from second nearest neighbor to the nearest neighbor of x. Then there are third nearest neighbor and 1/5 nearest neighbor which lie in the same cube. So, the frequency of exchange with them is denoted as K1. So, the K1 can be indicated like this, V to 3, and also to the 5th nearest neighbor from nearest neighbor is also denoted as K1. So, K1 is the frequency of exchange of the vacancy from nearest neighbor of x to third or 5th nearest neighbor of x. And then the vacancy can escape the first or second coordination shell of x by jumping from this second nearest neighbor onto the fourth nearest neighbor doesn't actually lie in the first or second coordination shell of x. It is inside the next cube, which is on the right hand side, the body center atom of right hand side, as I have shown here by number 4. This is denoted as K2. So, K2 is the frequency of So, by making a K2 jump, the vacancy is leaving the first or second coordination shell of atom X. So, remember, in BCC there is no common nearest neighbor for X and vacancy. The first and second coordination shell are either the second nearest neighbor or third and fifth nearest neighbor of X. So, this is important as we go further. So, keep this in mind, and any other frequency is denoted as omega 0. So, with this, let us try to evaluate cos theta I plus 1, the average value of it. So, let us redraw this BCC unit cell again, and now in this cell I have shown the tagged atom X at the body center of this cube, and suppose the first jump of the atom X is from this site A to X. So, the first jump of tagged atom X is from A to X. So, the second jump of X may be one of the 8 sites, and those 8 sites, the nearest neighbor of X, can be divided into sites of the types A, B, C or D. A is from where the X has just jumped during the first jump. The sites of type B are the ones onto which, if the second jump occurs, the cos theta with the first jump is going to be minus 1/3. Similarly, type C sites are making cos theta is equal to 1/3 with the jump vector Ax, and the side D, which makes the cos theta equal to 1. So, the second jump of X may be back onto side A, in which case cos theta A equal to minus 1, or it can be in one of the 3B type of sites, for which cos theta B is equal to minus 1/3, or it can be in one of the 3C type of sites, for which cos theta C is equal to plus 1/3, or it can be into side D, and cos theta D is equal to plus 1. So, if we want to evaluate average of cos theta I plus 1, this can be given as sigma I equal to 1 to Z Px s times cos theta s. So, Pxs here is the probability that the second jump of atom X is into the site S. So, cos theta s is the cosine of the angle between the second jump vector and the first jump vector, which was Ax. So, now there are 1A type of site, 3B types, 3C types and 1D type. So, we can expand this as, let us denote the average of cos theta I plus 1 as C, can be written as cos theta A is minus 1. So, minus Px of A minus, there are 3 B type of site and cos theta for each is minus 1/3. So, this would be minus Px of B, again 3 C type of sites, cos theta is 1/3. So, plus Px of C, and there is only one D site for which cos theta is 1, plus Px of D. Now, we need to evaluate the Px of S for each of the A, B, C and D. This can further be written as the row matrix of minus 1, minus 1, plus 1, plus 1, and the column matrix of Pxa, Pxb, Pxc, Pxd. And this we can write it as minus 1, minus 1, 1, 1, and this matrix can be denoted as Px of S. Now, we need to evaluate Px of S. Px of S is the probability that the atom X jumps into site S for its second jump. So, it can be written as the probability that a vacancy comes to site S after itself making n jumps times the probability that that vacancy actually exchanges with X. Now, let us call this probability that the vacancy arrives at X after itself making n jumps as Pn of S, and this probability of exchange of vacancy with X, we know if we go back to our frequency model, the frequency of exchange of vacancy with X is omega 2, and a vacancy can make 1 omega 2 type of jump, 3 omega 1 type of jumps and 4 K1 type of jumps. So, the probability that a vacancy will exchange with X is given by omega 2 divided by total number of jumps per second that the vacancy can make, which is the sum of omega 2, 3 omega 1 and 4 K1. So, this probability can be given as omega 2 over omega 2 plus 3 omega 1 plus 4 K1. Now, let us try to evaluate Pn of S for different types of sites. For example, Pn of A here is the probability that the vacancy after itself making n jumps will arrive on site A. Remember, when I am talking about the exchange of vacancy, I am considering the same vacancy with which atom X has exchanged during the first jump. That vacancy itself can make a number of jumps and arrive again on one of the nearest neighbor sites of X, and the X can exchange with it again, and those are the correlated jumps which will contribute to the average cos theta I plus 1. If at any time the vacancy goes far away and another vacancy comes as nearest neighbor of X and then X exchanges with that new vacancy, then the correlation sequence with the first vacancy is broken. So, in this particular problem, to make it simple, we are assuming that the vacancy is considered as escaped if it leaves its first or second coordination shell. that means the vacancy is assumed to be escaped if the vacancy is not on either first, second, third or fifth nearest neighbor of x. Everywhere else if the vacancy jumps, then we assume that the vacancy has escaped. Similarly, if from the outside, if vacancy arrives at any of these sites, first or second coordination shell of x, it will be taken as a random vacancy jump. So, for vacancy to exist at A after n number of jumps, the vacancy should have been on one of the nearest neighbors of A after n minus 1 jumps. Okay. So, if let me redraw this again here. So, I have redrawn the BCC cell here, but now I have also shown all of the nearest neighbor sites of A, because we want to evaluate Pn of A. So, after n minus 1 jumps, the vacancy should have been on one of these nearest neighbors of A, and on its nth jump the vacancy will exchange with A. Now, this nth jump may be of omega 1 prime type of jump or a k1 type of jump. Okay. Omega 1 prime type of jump is the jump from second nearest neighbor of x to the nearest neighbor of x, and k1 type of jump is the jump from third or fifth nearest neighbor of x to the nearest neighbor of x. So, I have shown three second nearest neighbor of x here by number 2, 3 third nearest neighbor by number 3, and the fifth nearest neighbor of x by number 5 here. So, let us consider these different types of jumps one by one. If we consider omega 1 prime type of jumps, so let us consider any of the nearest neighbor site of A, which is second nearest neighbor of x. So, let us consider this site first. So, Pn of A can be written as probability that the vacancy is on nearest neighbor site of A after n minus 1 jumps times the probability that the vacancy makes a omega 1 prime or k1 type jump during nth jump. Okay. So, let us first evaluate the omega 1 prime type of jump, that is from the second nearest neighbor, and then the k1 type of jump. So, we write Pn of A is equal to. Now, if you consider any of that second nearest neighbor atom of x, let us consider this atom 2 here. Now, for the vacancy to exist on this site after the n minus 2 jump, the vacancy should have been on one of the nearest neighbor sites of 2. And remember, this after n minus 2 jumps, now the vacancy can only be on either this A site or one of these two B sites or on C site, because the other 4 nearest neighbor of this atom 2 are outside the first and second coordination shell of x, and we are not considering those, because if the vacancy jumps from there, then it would be a random vacancy jump and will not be a part of this correlation effect. So, the only sites that the vacancy should have occupied after n minus 2 jumps are either A or one of the two B's or C. So, this we can write as Pn minus 2 of A plus 2 times Pn minus 2 of B plus Pn minus 2 of C, where Pn minus 2 of S denotes the probability that the vacancy arrives at site S after n minus 2 jumps. Now, we consider each of this type 2 site here. if we consider this site, again after n minus 2 jump, the vacancy should have been either on A or this to B or on C. And also for this 2 here, the vacancy should after n minus 2 jumps should have been either on A or this to B or on C. So we can multiply this by 3 times the probability on its n minus first jump, the vacancy exchanges with the type 2 atom, and this will be the jump from the nearest neighbor of X to the second nearest neighbor of X. So this will be an omega 1 type of jump, and the probability of that would be omega 1 divided by omega 2 plus 3 times omega 1 plus 4 times K1, and for its nth jump, vacancy has to jump from this type 2 to A, and this is a jump from second nearest neighbor to the nearest neighbor. So it is an omega 1 prime type of jump. So the probability of that would be given by omega 1 prime type, and when the vacancy is on 2, it can either make a jump onto the one of the 4 nearest neighbors of X, or it will make a jump onto one of the 4th nearest neighbor of X, which are not shown in this figure. So those will be K2 type of jumps. So the probability of omega 1 prime type of jump would be omega 1 prime divided by 4 omega 1 prime plus 4 K2. Now the vacancy after n minus 1 jump could have been on the third nearest neighbor, that is on one of these 3 type 3 sites. Now for vacancy to exist on this site, let us consider this type 3 site here first. After n minus 1 jump, the vacancy should have been on one of the nearest neighbors of this 3 atom, only 2 of which, that is A and B, lie on the first and second coordination shell of X here. The others will be outside it, and so we won't consider those. So this would be Pn minus 2 of A plus Pn minus 2 of B. Then for this type 3 atom, after n minus 2, vacancy should have been either on this A or on this B. So again Pn minus 2 of A plus Pn minus 2 of B, and for this it should have been either on this A or this B. So this should be Pn minus 2 of A plus Pn minus 2 of B times the probability that on the n minus first jump, the vacancy exchanges from, let us say, this type from A to type 3 atom. This is a jump from nearest neighbor onto the third nearest neighbor. So this is a K1 type of jump. So the probability of that would be K1 over omega 2 plus 3 omega 1 plus 4 K1, and on nth jump the vacancy has to exchange from this 3 to A. Now this is from third nearest neighbor to A nearest neighbor. This would be counted in any other type of jump. So this is basically a random jump, because other jumps are much away from atom X, and so the probability of jump from type 3 atom to any of the nearest neighbor is 1/8, because there are 8 nearest neighbor. So this should be multiplied by 1/8 here. Now there is one more nearest neighbor of A, which is type 5, or the 5th nearest neighbor of X. Now for the vacancy to be at type 5 after n minus 1 jump, it should have been on A only after n minus 2 jump, because that is the only nearest neighbor of type 5 which lies in first or second coordination shell of X. Any other vacancy would have been a lost vacancy, and so those will not be considered. And so for this we can write as P n minus 2 of A times, again this will be a K1 type of jump. So, K1 over omega 2 plus 3 omega 1 plus 4 K1 times 1 over 8. Let us call this factor as F2 and this as F3. So, our F2 is omega 1 times omega 1 prime divided by omega 2 plus 3 omega 1 plus 4 K1 times 4 times omega 1 prime plus K2, and F3 is K1 over 8 times omega 2 plus 3 omega 1 plus 4 K1. Let us now consider Pn of B, that is the probability that the vacancy arrives at site B after itself making n jumps. So, I have shown type B site. Let us consider this type B site here. I have also shown all the nearest neighbor of this type B site here, out of which there are 3 second nearest neighbor of X which are shown by number 2 here. 3 are third nearest neighbors and 1 is the fifth nearest neighbor. It is shown by number 5 here. So, first type of jump, if we consider for B, we can write Pn of B is equal to, so the jump from second nearest neighbor to the nearest neighbor. So, this will be an omega 1 prime type of jump, and for being on type 2 site after n minus 1 jump, the vacancy should have been on, if we consider this type 2 site, this should have been on either A or 2 B sites or 1 C site after n minus 2 jumps. So, we can write P n minus 2 of A plus 2 times P n minus 2 of B plus P n minus 2 of C times the factor F2 which we have defined above. If we consider this type 2 site, again after n minus 2 jump, the vacancy should have been on either these 2 B sites or on this A site or on this C site. So, P times n minus 2 of A plus 2 times P n minus 2 of B plus P n minus 2 of C times F2 plus, if I consider this type 2 site, then the vacancy after n minus 2 jumps should have been either on this side B or one of these 2 sites C or on side D. So, this would be P n minus 2 of B plus P n minus 2 of C, and there are 2, so 2 times, plus P n minus 2 of D times F2. For the vacancy to be on third nearest neighbor, let us consider this one first. After n minus 2 jumps, the vacancy should have been either on A or B. So, this should be P n minus 2 of A plus P n minus 2 of B times F3. For this type 3, the vacancy should have been on either this B or this C. So, P n minus 2 of B plus P n minus 2 of C times F3 plus for this type 3, the vacancy should have been either on this B or this C, Pn minus 2 of B plus Pn minus 2 of C times F3, and for this jump from 5, after n minus 2 jump, the vacancy could have been only on side B here, because any other jump would have been a random jump, because it would be from outside the coordination shells of X. So, this would be Pn minus 2 of B times F3. So, if we write Pn of A and Pn of B here again, Pn of A we can write as 3 times Pn minus 2 of A times 6 Pn minus 2 of B times 3 Pn minus 2 of C times F2 plus 1, 2, 3 and 4 times Pn minus 2 of A times F3 for B 1, 2, 3, 3 times Pn minus 2 of B times F3. Okay. So, Pn of A can be written as 3 times. Similarly, Pn of B can be written in terms of F2 and F3 as now for the C and D type we can apply the similar treatment, and in fact we can get it by applying this inverted symmetry here, because this cube has an inverted symmetry about point X. So, whatever we apply for A and type B sides by inverted symmetry we can apply to type C and D sides. Now, we can write this, and so we can also get the equations for Pn of C and Pn of D, and we can write those in the form of matrices. So, we can write the matrix of Pn of A, B, C, D, Pn of A, Pn of B, Pn of C and Pn of D is equal to, first the factor of F2 times, we can form a 4 by 4 matrix and multiply it by the column matrix of Pn minus 2 of S. So, the 4 by 4 matrix elements we can write from these two equations as 3, 3, 6, 3, 0, and we have 2, 5, 4, 1 times the column matrix of Pn minus 2 of A, Pn minus 2 of B, Pn minus 2 of C, Pn minus 2 of D. Now the remaining elements we can write by inversion symmetry, and so the last two rows we can just write as 1 4 5 2 and 0 3 6 3 plus the term in F3. Here the matrix we can write as 4 3 0 0 and 1 4 2 0 1 4 2 0. So this one we can write at 0 2 4 1 0 0 3 4 times the matrix of Pn minus 2 of ABCD. So we can write this as Pn is the matrix of Pn of S. This F2 times the matrix we can write as Q1 Pn minus 2 plus F3 times this matrix we can write as Q2 Pn minus 2. So which would be Q times Pn minus 2, where Q is Q1 plus Q2 and Q1 is F2 times 3 6 3 0 2 5 4 1 1 4 5 2 6 3. So if we substitute, if we go back to the equation for C, we had got C is equal to this matrix times Px of S, and we got Px of S is equal to Pns times omega 2 over omega 2 plus 3 omega 1 plus 4 k1. So we can write C as and let us call this term as F1. So C is equal to F1 times Pn, where we denote F1 as minus 1 1 1, the row matrix times the probability of omega 2 type of jump. Now we can write Pn as Q times Pn minus 2. Pn minus 2 can be expressed as Q times Pn minus 4. So this becomes Q square times Pn minus 4, and if we continue this we would get Pn is equal to Q to the power n by 2 times Pn minus n would be P0, and P0 here is the probability matrix that the vacancy exists at site S after 0 jump, after 0 jumps of vacancies, that is right after the first jump of X. And we know right after the first jump the vacancy exists at A. So, P0 of only A is equal to 1, and P0 of all other sides should be 0. So, the matrix P0 essentially is 1 0 0 0, and n by 2 we can replace with m, and so we can write Pn is equal to q to the power m times P0. Now, when we write the expression for C, we are writing F1 times Pn, but n can vary from 1 to infinity, because for some atom the vacancy will arrive after making 2 jumps, for some atoms it will arrive after making 10 jumps, for some atoms it will arrive after making 1000 jumps, and we have to consider all such correlations, and so n has to vary from 1 to infinity. So, this we have to take actually as summation for n equal to 1 to infinity. So, we can write the expression for C as C equal to summation n equal to 0 to infinity F1 times q to the power m times P0. Now, let us try to evaluate what is F1 times q to power m. So, if we first evaluate F1 times q, that is going to be omega 2 over omega 2 plus 3 omega 1 plus 4 k1 times minus 1 1 1, and q is nothing but q1 plus q2. q1 is F2 times the matrix 3 6 3 0 2 5 4 1 1 4 5 2 0 3 6 3 plus F3 times the matrix 4 3 0 0 1 4 2 0 0 2 4 1 0 0 3 4. If we multiply this row matrix and this 4 by 4 matrix, we will get minus 3 minus 2 minus 5 plus 1 minus 4 plus 0 minus 4. So, if we do this, we will notice we will end up getting the product to be equal to omega 2 over omega 2 plus 3 omega 1 plus 4 k1 times minus 1 1 1 times 4 F2 plus 5 F3, and again this is nothing but F1. So, we get F1 times q is equal to 4 F2 plus 5 F3 times F1. So, if we take F1 times q square, that should be F1 times q times q. So, this would be 4 F2 plus 5 F3 square times F1 and so on. So, if we get F1 times q to power m, that should be equal to 4 F2 plus 5 F3 to the power m times F1. So, if we substitute in this series, we get equation for C as C is equal to sigma. Since now we are calling n by 2 as m, and n is a very large number, so we can replace this with m equal to 0 to infinity and F1 times P0, if we evaluate, this should be omega 2 over we will get minus omega 2 over omega 2 plus 3 omega 1 plus 4 k1, and we will end up getting C equal to minus omega 2 over omega 2 plus 3 omega 1 plus 4 k1 times summation m equal to 0 to infinity 4f2 plus 5f3 to the power m. Now this series we can approximate as 1 over 1 minus 4f2 minus 5f3, and then if we substitute for f2 and f3 and simplify, we will get the expression for C, which is nothing but average of cos theta I plus 1 for BCC as minus omega 2 over omega 2 plus 3 omega 1 plus 3.375 k1 minus omega 1 prime over omega 1 prime plus k2, which can also be written as minus omega 2 over omega 2 plus 2 omega 1 plus 3.375 k1 plus omega 1 k2 over omega 1 prime plus k2. The second expression is the one which was derived by Manning. Note there is a little bit of correction in Manning's paper. This should have been omega 1 prime there. Okay, so this is the expression for average cosine of I plus 1 in a BCC lattice. So now let us look into the second problem. In this problem, the probability of a vacancy starting at A and returning to one of A, B, C, D or E sites is given, which are these probabilities are respectively alpha, beta, gamma, delta and epsilon, and we have to find out the probability that a vacancy starting at one of the B sites returns to A, B, C, D or E type of site. To evaluate this, because of the symmetry, we can reorient our cube, which is shown here, such that our B site now becomes an A site, and we redistribute the other nearest neighbors of X in the types A, B, C, D and E. So let us call the reorientation as types A1, B1, C1 and D1. So let us say my this site B is now type A1. So I have shown the new distribution with the yellow color here. So the 4 B sites are B1, 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 B1. The 2 C sites are C1, C1. The 4 D sites are D1, D1, D1 and D1, and then E site is located here. Now the probability that a vacancy starting at a site B returns to A is same as probability of a vacancy starting at A1 and returning to a B1 type of site, which should be equal to beta. Vacancy starting at B and returning to one of the B sites is same as vacancy starting at A1 and returning to either A1, B1, C1 or D1. So that should be equal to, so this probability should be alpha plus beta plus gamma plus delta. Vacancy starting at B and returning to one of the C sites is same as vacancy starting at A1 and returning to either B1 and D1. So which is beta plus delta. And vacancy starting at B site and returning to one of the D sites is same as vacancy starting at A1 and returning to either B1 type, C1 type, D1 type or E1 type. So, this should be equal to beta plus gamma plus delta plus epsilon, and vacancy starting at B and returning to an E site is same as vacancy starting at A1 and returning to D1. So, this should be equal to delta. Now, this is how we can find the new probabilities. Now, where is this useful? Remember, when we derived the expression for correlation factor for FCC, we considered any vacancy moving out of the nearest neighbor coordination shell of the tagged atom as being escaped. But there is a finite probability that the vacancy will return to any one of the nearest neighbor site of x after making n jumps, and it can return from second coordination shell or third or fourth or even from a far distance. And if we want to be more accurate in calculating the correlation factor, we need to know these probabilities. Now, once we know these probabilities, we can find the correlation factor more accurately, and there we will need to convert from one starting position of the vacancy to another starting position based upon the knowledge of one set of probabilities. Okay. So, there this would be useful. So, these are the two problems we solved today. Thank you.